All right. So nowadays, when we think about the atom, we think about the quantum model of the atom. And that's the kind of most accurate model because it gives us the most accurate predictions. And you can see this little timeline here. It started with John Dalton when he first discovered kind of atoms. And he just thought that they were just basically a solid sphere. After that, J.J. Thomson found out actually it's not a solid sphere. There's a lot of empty space around it. But he thought that there was just a big kind of nebulous of positive charge. Rutherford found out that we have a nucleus right in the center, and then we have electrons kind of floating around our atom. Niels Bohr found out that these electrons can only be in certain orbits and that our atoms are quantized. However, he still thought of as electrons as particles, and so they're kind of they're only at one location. And then finally, Schrodinger and other scientists, right, developed the quantum model of the atom. And so basically here we have our positively charged nucleus, and then we have our electrons still in kind of orbits, but we don't know exactly where these orbits are. So they're just more probability charts. Right, so it says right there, electrons don't move around the nucleus in orbits, but in clouds where their position is uncertain. And right now, this is the most accurate model of the atom. For us, the Bohr model is very good as well, so that'll work for most of our applications. But when we get into higher level stuff, or if you decide to take it further, in order to get the most accurate predictions and the most accurate view of what is really going on, you need to take a look at the quantum model. So as we said in the last video, right, we have the uncertainty principle. So we can't know about the exact location and position of the electron at once. And if we think about which one we want to know more, we want to know more about the energy. So generally, we care about the energy of an electron more than the position. And the way that we figure out the energy of an electron is through the use of the Schrodinger equation. And so that just looks like something like this. We're not going to go through it a lot. Again, this is some higher level math, but I just want to introduce the topic. This is what's known as a Hamiltonian. It's an operator, so it's going to basically do a bunch of mathematical operations on some other function. This little psi here is the wave function. So we're thinking about an electron as a wave. And when we solve for the Schrodinger equation, we can get a whole lot of energy levels here. And so when we solve this, solving leads to orbitals. This is what our wave function kind of looks like, and this is what's going to predict where our electron most likely is when it has this certain energy level. So we'll just say where an electron is housed, right? And it's a probability distribution. And so we're going to learn about these orbitals, these electron houses next, because they have a lot of predictive properties with them. So we're going to think of this as a kind of like an address. You can think about your own address, right? You've got, you live in the United States, then California, and then your specific city, then your specific, street, and then the specific number. Electrons are also housed in these orbitals, and we go from more general to more specific. And so instead of having kind of a zip code and state and that kind of stuff, we have quantum numbers. And these quantum numbers we'll learn about in a little bit are M, L, M sub L, and M sub S. And we get more and more specific as we go down. As I said, the quantum mechanics is not a simple topic, and so we're just really giving a brief overview. But the really cool thing about quantum mechanics is how well it works. So for example, we have the periodic table. And the periodic table, for the most part, was discovered before quantum mechanics. And it was just based and organized based on observed properties. So for example, they noticed, hey, beryllium, magnesium, calcium, strontium, barium, and radium all like to be a +2 charge. Everything here likes to be a +1 charge, like we learned before. And so we're going to put them in the same column. Why do they like to be that charge? Well, we don't really know. We're not looking at that. This is just the what behind it, right? So they're just taking observations and they're organizing them. However, we as scientists don't want to know just the what, we want to know the why, and that's where quantum mechanics comes in. So quantum mechanics explains the why behind the periodic table and a lot of other things. And so the super cool part is that these two match perfectly, or almost perfectly. And so by understanding the why, we can make predictions about some stuff that we don't know, some stuff that's hard to measure. And so we're mostly going to be focusing on the what in this course, but the why is also important.